May 1945, Annapolis, Maryland. In a naval laboratory warehouse near the Chesapeake Bay, a long cylindrical object rested on steel supports beneath harsh overhead lights. Its aluminum skin was scarred, its paint chipped by transport across a defeated continent and an ocean. To the officers and engineers gathered around it, the object was a captured German weapon, catalogued, tagged, and stripped of any remaining danger. To the man standing silently beside it, it was something far more unsettling. Dr. Robert Hutchings Goddard did not speak as he moved slowly along the length of the rocket. At 62 years old, weakened by throat cancer that had reduced his voice to a rasp, Goddard conserved his words carefully. He did not need to speak to understand what he was seeing. The dimensions alone told the story. 46 feet tall, nearly 14 tons at launch. A vehicle designed not as an experiment, not as a laboratory curiosity, but as a mass-produced, operational ballistic missile. For more than 2 decades, Goddard had been America's most persistent advocate of liquid-fueled rocketry. He had launched the world's first such rocket in 1926 from a frozen field in Massachusetts. He had solved problems of stabilization, fuel injection, and combustion that most physicists considered theoretical curiosities at best. He had filed patents, written papers, and quietly conducted tests in the deserts of New Mexico. And for most of that time, the United States government had ignored him. Now, in this warehouse, the consequences of that indifference stood before him. The German rocket designated Aggregate 4, known to the world as the V-2, was not merely larger than anything Goddard had built. It represented a scale of engineering commitment that the United States had never applied to rocketry before the war. Goddard ran his hand along the fuselage, feeling the cold metal beneath his fingers. He immediately recognized familiar concepts: liquid oxygen and alcohol propellants, gyroscopic stabilization, thrust vector control. These were ideas he had pioneered years earlier, often in isolation, often underfunded, sometimes ridiculed in the press. But recognition brought no satisfaction, only realization. This rocket was not the product of a lone inventor. It was the output of an industrial system. For years, American military planners had assumed that Germany's so-called wonder weapons were extravagant distractions, symbols of a regime chasing technological miracles while losing a conventional war. Jet aircraft, rockets, advanced submarines. These were often dismissed as impressive prototypes that arrived too late to matter. The United States, with its vast factories and unmatched production capacity, believed it had won the war through superior organization and overwhelming material output. Science, in this view, followed industry. The V-2 challenged that assumption. What stood in Annapolis was not a prototype rushed into service. It was the end, product of a coordinated national effort that began in the early 1930s, matured through systematic testing, and reached full industrial production under wartime conditions. By the time American forces crossed into Germany in 1945, the V-2 was being produced at a rate of approximately 600 missiles per month. Each one contained more than 50,000 individual components. Each one embodied solutions to engineering problems that American laboratories had barely begun to confront. Goddard did not yet know the full extent of that gap, but he sensed it. 20 years earlier, he had warned that rockets could one day deliver payloads across continents. In 1919, his paper, A Method of Reaching Extreme Altitudes, had proposed not only high-altitude research, but the theoretical possibility of long-range rockets. The response from the American scientific establishment had been lukewarm at best, hostile at worst. Newspapers mocked the idea of rockets reaching space. Military officials saw no immediate application. Funding came sporadically, often from private patrons rather than public institutions. Germany, meanwhile, had drawn different conclusions. In the aftermath of World War I, German engineers and physicists began exploring rocketry as a way to circumvent the restrictions imposed by the Treaty of Versailles. Artillery ranges were limited. Aircraft development was monitored. Rockets, by contrast, fell into a gray area. By the early 1930s, the German Army Ordnance Office recognized their potential and began funding research. In 1932, a young engineer named Wernher von Braun joined the effort. By 1934, German experimental rockets had already surpassed the altitudes achieved by Goddard's designs. None of this was widely understood in the United States during the war. Intelligence reports focused on immediate threats: U-boats in the Atlantic, aircraft production, armored divisions. When reports of long-range rockets surfaced, they were often discounted or treated as psychological warfare. Even after the first V-2 struck London in September 1944, killing civilians without warning or defense, many American analysts regarded the weapon as militarily inefficient, a terror device rather than a strategic system. That view rested on a dangerous assumption. The assumption was that technological leadership was automatic, that American scientific talent, combined with industrial capacity, guaranteed superiority across all domains, that breakthroughs would emerge naturally when needed, without sustained investment or centralized direction. Goddard himself had lived under that assumption for much of his career, believing that demonstrable success would eventually bring institutional support. The rocket in Annapolis proved otherwise. As Army ordnance officers and Navy engineers began cataloging the V-2, they uncovered layers of sophistication that defied easy explanation. This was not simply a large rocket. It was a machine that integrated propulsion, guidance, materials, science, and manufacturing precision into a coherent whole. The engine alone produced approximately 60,000 pounds of thrust, more than 60 times the output of Goddard's most powerful experimental motor, which had reached 985 pounds after years of work. The implications were immediate and troubling. The United States had entered the war without a ballistic missile program. Its rocket efforts were fragmented across universities, small military laboratories, and private inventors. There was no equivalent to Peenemünde, the massive German research center on the Baltic coast, where thousands of scientists, engineers, and technicians worked exclusively on rocket development. There was no centralized doctrine for missile warfare, no production infrastructure designed to build rockets at scale. Standing beside the V-2, Goddard understood that the gap was not measured in months, it was measured in years. He also understood something more personal. Many of the principles embodied in the German rocket were concepts he had developed and patented decades earlier. Regenerative cooling, turbine-driven fuel pumps, gyroscopic stabilization. In a letter written shortly after examining the V-2, Goddard would express a restrained bitterness, noting that the Germans had taken ideas similar to his and carried them forward with resources he had never been granted. Yet even this observation missed a crucial point that younger American engineers were beginning to grasp. The Germans had not simply borrowed ideas. They had built a system capable of turning ideas into weapons. The V-2 was the visible artifact of that system. Its existence challenged the comforting narrative that American victory automatically implied technological primacy. In reality, the United States had won the war while remaining dangerously underdeveloped in one of the most consequential fields of future warfare. As word of the V-2's capabilities spread through classified channels in Washington, a shift began. Reports circulated within the War Department and the Navy's Bureau of Ordnance, warning that rocket technology would not remain a curiosity. Ballistic missiles offered a means of delivering warheads at supersonic speeds, beyond the reach of existing defenses. The war had ended, but a new strategic competition was already taking shape. The assumption that America could afford to ignore rockets had collapsed. Goddard would not live to see how fully that realization reshaped national policy. He died in August 1945, just months after his visit to Annapolis. But the moment he stood before the V-2 marked a turning point, not only for American rocketry, but for the way the United States understood the relationship between science, industry, and national power. The rocket in that warehouse was not a trophy. It was a warning. And as American forces continued to uncover the infrastructure behind it, factories, documents, test stands, and thousands of trained specialists, that warning would grow louder, impossible to ignore. The question facing the United States was no longer whether rockets mattered. It was whether the nation could build the system required to catch up. To understand why the V-2 represented such a profound shock to American engineers, it was not enough to examine the rocket itself. The missile was only the visible surface of something far larger. Beneath it lay an entire system, organizational, industrial, scientific, and political, that had sustained German rocketry for more than a decade before the first V-2 ever fell on London. The contrast between that system and the one that existed in the United States in 1945 could not have been sharper. In Germany, rocket development had become a state priority long before the war turned global. In the early 1930s, as the Weimar Republic struggled under economic collapse and political instability, German military planners were already searching for technologies that could restore strategic leverage without violating the letter of the Treaty of Versailles. Rockets offered precisely that opportunity. They were not artillery. They were not aircraft. They occupied a space the treaty's authors had never anticipated. By 1932, the German Army Ordnance Office had established a formal rocket research program. Young engineers and physicists were recruited directly from technical universities. Among them was Wernher von Braun, a 20-year-old engineering student whose interest in spaceflight aligned neatly with military requirements for long-range weapons. The program moved quickly. By 1934, experimental rockets designated A-2 were successfully launched from the island of Borkum, reaching altitudes that exceeded any achieved by American designs to that point. This progress was not accidental. It was the result of centralized direction and sustained funding. In 1936, the German military authorized construction of a dedicated rocket research center at Peenemünde on the Baltic coast. The site covered more than 25 square kilometers. It included test stands, wind tunnels, manufacturing halls, laboratories, housing for thousands of personnel, and its own power generation facilities. By the early 1940s, Peenemünde employed approximately 6,000 engineers, technicians, and support staff, supported by tens of thousands of workers in associated factories across Germany. Nothing remotely comparable existed in the United States. Robert Goddard conducted most of his work with a handful of assistants, often fewer than 10 at any given time. His test facilities consisted of improvised stands in remote desert locations. Funding came from private sources, primarily the Guggenheim Foundation, amounting to tens of thousands of dollars per year rather than millions. Military interest remained intermittent and cautious. Even as late as 1941, American rocket research was divided among small Army, Navy, and university programs with limited coordination. The German system, by contrast, was unified. Peenemünde was not merely a research center. It was the hub of a national industrial network. Design work, testing, production planning, and operational deployment were integrated under military oversight. Problems discovered in testing could be communicated directly to manufacturing facilities. Feedback from combat launches informed design revisions. Engineers, machinists, metallurgists, and physicists worked within the same organizational framework, sharing data and priorities. This integration allowed the Germans to move from experimental rockets to an operational weapon system in a remarkably short time. The A-4 rocket, later renamed the V-2 for propaganda purposes, first flew successfully on October 3, 1942. Within 2 years, it was being produced in large numbers and deployed against enemy cities. That transition, from prototype to mass production, was made possible by an industrial commitment equivalent in scale to the American Manhattan Project. German records indicate that the V-2 program consumed resources rivaling those allocated to atomic research in the United States. Specialized machine tools were developed solely for rocket components. Entire factories were reconfigured to produce turbopumps, gyroscopes, and combustion chambers. When Allied bombing threatened surface facilities, production was moved underground rather than abandoned. The Mittelwerk complex near Nordhausen exemplified this commitment. Built into the Harz Mountains, its tunnels extended for miles. Inside, production lines assembled V-2 rockets under conditions of extreme secrecy. Each missile incorporated approximately 50,000 individual parts, many of which required tolerances measured in thousandths of an inch. Despite wartime shortages and bombing campaigns, the Germans achieved a production rate of roughly 600 rockets per month by late 1944. This was not improvisation. It was industrialization. The American system had never been asked to do anything similar. Before 1945, no U.S. agency had attempted to manufacture large, liquid-fueled rockets at scale. Experimental engines existed, but they were laboratory devices, not production models. Guidance systems remained rudimentary. Materials suitable for sustained high-temperature operation were in limited supply. Most critically, there was no unified program to integrate these elements into a single operational weapon. German doctrine, however, treated rocketry as a comprehensive discipline. Propulsion engineers worked alongside metallurgists to solve high-temperature combustion problems. Specialists in fluid dynamics addressed fuel injection and cooling. Precision instrument makers developed gyroscopes capable of surviving launch stresses. Electrical engineers designed control circuits that functioned reliably under vibration and acceleration. Every subsystem was developed with mass production and operational reliability in mind. This philosophy was visible in the V-2's design. The rocket was not optimized for minimum weight. Instead, it was deliberately overbuilt. Structural components featured generous safety margins. Redundancy was incorporated into fuel lines and electrical systems. The goal was not elegance, but survivability. The missile had to function after transport, handling, and rapid deployment by field crews operating under combat conditions. American engineers examining captured components were struck by this approach. In peacetime U.S. industry, cost and material efficiency often dictated design choices. In Germany's rocket program, performance and reliability took precedence, even when that meant increased complexity or weight. This reflected a system that could allocate scarce resources selectively to priority projects. Equally important was the German approach to testing. Between 1937 and 1945, the German rocket program conducted thousands of test firings. Early failures were analyzed systematically. Components were redesigned, retested, and reintroduced. Entire test stands were destroyed by explosions and rebuilt. Each failure contributed data that informed subsequent designs. By the time the V-2 entered operational service, its major subsystems had been refined through repeated iteration. The United States lacked this experiential base. American engineers in 1945 had conducted only a handful of liquid rocket launches. Failures were rare, not because designs were robust, but because test opportunities were limited. There was little institutional memory, little accumulated knowledge about what worked and what did not at scale. When American reports later estimated that the Germans had conducted approximately 6,000 test and combat launches, the number underscored just how far ahead they were in practical experience. Training was another critical difference. German engineers were not isolated specialists. Many rotated through multiple roles over the course of the program. A guidance engineer might observe test launches. A propulsion specialist might consult on manufacturing issues. This cross-disciplinary exposure fostered a shared understanding of system-level behavior. Problems were addressed holistically rather than in isolation. In the United States, by contrast, scientific work was often compartmentalized. University researchers focused on theory. Military laboratories focused on specific components. Industrial firms focused on manufacturing contracts. Coordination existed, but it lacked the unity and urgency that characterized the German effort. This difference was not a matter of intelligence or creativity. American scientists were fully capable of understanding the physics involved. The gap lay in organization and commitment. Goddard's career illustrated this perfectly. Many features of the V-2 mirrored concepts he had demonstrated years earlier. Regenerative cooling, turbine-driven pumps, gyroscopic stabilization. These were not foreign ideas. What America lacked was the institutional framework to develop them simultaneously, at scale, under sustained military direction. German leadership, for all its moral bankruptcy, recognized the strategic value of such a framework. By 1943, the V-2 program had been elevated to the status of a national priority. Resources were diverted from conventional weapons. Skilled labor was reassigned. Even as Germany faced defeat on multiple fronts, rocket production continued. This decision reflected a belief that technological breakthroughs could offset strategic decline. That belief was flawed in its immediate military effect. The V-2 did not alter the outcome of the war, but it succeeded spectacularly in demonstrating what was technologically possible. When American forces finally gained access to Peenemünde, Mittelwerk, and associated facilities in 1945, they encountered not a desperate last stand of experimental engineering, but the remnants of a mature industrial ecosystem. Drawings were standardized, components were cataloged, procedures were documented. The Germans had built a pipeline from concept to deployment. For American observers, this realization was sobering. The United States had assumed that its scientific leadership was inherent and self-sustaining. The German rocket program revealed that leadership had to be cultivated deliberately. Talent alone was insufficient. It required funding, infrastructure, coordination, and political will. The system that sustained the V-2 had been constructed deliberately over more than a decade. Dismantling it had taken only months. Recreating something comparable in the United States would take years. By the summer of 1945, as reports from captured facilities circulated through Washington, this conclusion was unavoidable. The challenge facing America was not simply to study German technology, but to build an equivalent system, one capable of turning theoretical knowledge into operational capability. The rocket in Annapolis was the artifact, The system behind it was the real revelation. And as American planners began to understand that system in detail, they would soon discover that the gap was even wider than they first imagined. The illusion that the V-2 was merely an exotic German weapon began to collapse in April 1945, not in a laboratory, but beneath a mountain. On April 11th, units of the United States 3rd Armored Division pushed into the Harz Mountains of central Germany. Their objective was routine by the standards of the final weeks of the war. Secure transportation routes, clear remaining resistance, and locate any military installations before Soviet forces advancing from the east could reach them. Intelligence suggested weapons depots in the area. No one anticipated what lay beneath the hills near the town of Nordhausen. Hidden behind blast doors and guarded by fading SS units was the Mittelwerk underground factory complex. As American soldiers descended into the tunnels, their flashlights revealed a scene that defied every assumption about Germany's industrial condition. The tunnels extended for miles, carved directly into solid rock. Rail tracks ran through vast caverns where partially assembled rockets rested on stands. Crates of components were stacked in orderly rows. Entire production lines stood frozen in time, abandoned only days earlier. For the infantrymen, the shock was immediate but difficult to articulate. For the ordnance officers who followed, the implications were unmistakable. Major James Hamill of the U.S. Army Ordnance Corps walked the length of the tunnels with growing unease. This was not a research facility. This was mass production. Records recovered on site indicated output approaching 600 V-2 rockets per month at peak production. Each missile incorporated approximately 50,000 parts, many machined to tolerances tighter than those used in American aircraft engines. What made the discovery even more disturbing was how close this operation had come to continuing uninterrupted. The Mittelwerk facility had been designed specifically to survive Allied bombing. Above ground, Peenemünde had been damaged by air raids in 1943. The German response was not to abandon rocket production, but to move it underground, deeper than any bomb could reach. Here, shielded by hundreds of feet of rock, the V-2 program had matured into an assembly line operation. The cost of that decision was visible everywhere. American soldiers encountered prisoners from the Dora Mittelbau concentration camp, emaciated, exhausted, many barely alive. Tens of thousands had been forced to work in the tunnels under brutal conditions. Disease, starvation, and execution were routine. Post-war investigations would reveal that more people died building the V-2 than were killed by the rockets themselves in combat. This was the first fracture in the American understanding of the German rocket program. The V-2 was no longer an abstract technological achievement. It was a system sustained by industrial brutality, vast resources, and relentless prioritization. The scale of commitment shattered the notion that Germany had pursued rockets as a desperate gamble late in the war. This had been a long-term investment, maintained even as the Reich collapsed on every front. The second fracture came almost immediately after. Captured documents revealed that the Mittelwerk was only one node in a larger network. Components were manufactured across Germany, then transported underground for final assembly. Specialized factories produced turbopumps, gyroscopes, valves, and wiring harnesses. Quality control procedures were documented in detail. Serial numbers tracked components through the production process. This level of organization forced American officers to confront an uncomfortable reality. Germany had solved not only the physics of rocketry, but the logistics of manufacturing it under wartime conditions. Time now became the critical factor. Under the agreements reached at Yalta, much of central Germany was scheduled to fall within the Soviet occupation zone. Nordhausen lay perilously close to that boundary. Every document, every component, every intact rocket left behind would soon belong to the Red Army. Within hours of the discovery, urgent messages were sent up the chain of command. Colonel Holger Toftoy, chief of the rocket branch of the Army Ordnance Corps, received direct instructions from Washington. The directive was simple and uncompromising. Secure the rockets, secure the documents, and remove them before the Soviets arrived. What followed became known as Special Mission V-2. American troops, engineers, and logistics units worked continuously for weeks. Railway cars were brought into the area. Cranes were assembled inside the tunnels. Entire production lines were dismantled piece by piece. Technical drawings were boxed by the ton. Completed and partially completed rockets were loaded under armed guard. By the time the operation concluded, 341 rail cars had been filled with V-2 components and documentation. The captured hardware was sufficient to assemble approximately 100 complete rockets. The destination was Antwerp, where Liberty ships waited to transport the cargo across the Atlantic. This operation marked the third fracture in American assumptions. Until this point, the United States had viewed advanced weapons primarily as battlefield threats. Now, they were strategic assets. The race was no longer between America and a defeated Germany. It was between America and the Soviet Union. When the first shipments arrived at White Sands Proving Ground in New Mexico in late May 1945, Army engineers began the painstaking task of cataloging what had been captured. Crates were opened, components were laid out, drawings were translated and compared. With each examination, the gap between American expectations and German reality widened. The V-2's overall dimensions were impressive, but it was the internal systems that caused concern. The propulsion system revealed an engine producing approximately 60,000 pounds of thrust. American engineers, accustomed to Goddard's experimental motors, struggled to comprehend the leap in scale. More troubling was not the thrust figure itself, but the consistency. The Germans had achieved this performance repeatedly, in engines intended for mass production, not laboratory demonstration. Guidance systems presented another shock. The V-2 did not rely on simple ballistic trajectories. It employed gyroscopes and accelerometers, linked to an analog computer that actively controlled the missile's flight. This system measured acceleration, integrated velocity, and shut down the engine at a predetermined point. The concept existed in American theory. The execution did not. Perhaps most disturbing was the quality of manufacturing. American engineers noted that components subjected to extreme stress were overbuilt rather than minimized. Electrical wiring was meticulously routed and shielded. Fuel lines incorporated redundancy. Fasteners were uniform and standardized. These were design choices made by engineers who expected their weapons to be handled roughly, deployed quickly, and still function reliably. The cumulative effect of these discoveries was destabilizing. Each crate opened at White Sands chipped away at the belief that American science stood at the forefront of all advanced technologies. The Germans had not merely solved known problems. They had identified and addressed challenges American engineers had not yet encountered. The final fracture came with a realization that could not be ignored. Germany had developed this system under wartime constraints, with its cities bombed, its resources dwindling, and its transportation network under constant attack. Yet it had still managed to sustain a rocket production program of extraordinary complexity. The United States, by contrast, had enjoyed unmatched industrial capacity throughout the war, and had chosen not to apply it to rocketry. By the summer of 1945, internal Army and Navy reports began using language that would have been unthinkable a year earlier. Phrases such as technological surprise, critical vulnerability, and strategic deficiency appeared with increasing frequency. Analysts warned that ballistic missiles represented a category of weapon for which existing defenses were ineffective. The V-2 had exposed a blind spot. It was now clear that the gap was not theoretical. It was practical, measurable, and immediate. American engineers could understand what they were seeing, but understanding alone did not close the distance. Experience, infrastructure, and production capacity could not be improvised. The fractures in American assumptions had become irreparable. The question was no longer whether the United States had fallen behind in rocketry. That was now beyond dispute. The question was how, and at what moral and political cost, the nation would attempt to close the gap before another power did so first. By early summer 1945, the United States was no longer merely studying the German V-2. It was racing it. The collapse of American assumptions about rocket technology had produced an urgent shift in priorities inside the War Department. What had begun as an intelligence exploitation effort now evolved into an improvised crash program. The goal was no longer understanding for its own sake. It was operational parity before the next war began. At White Sands Proving Ground in the Tularosa Basin of New Mexico, crates marked only with serial numbers and German technical codes were unloaded under armed guard. Engineers from the Army Ordnance Corps, the Navy Bureau of Aeronautics, the Jet Propulsion Laboratory, and several university research groups converged on the desert facility. They were joined by a small but growing contingent of German engineers, captured at Peenemünde and Mittelwerk, now operating under strict military supervision. The first American attempt to translate German mastery, operational capability came quickly, and failed just as quickly. On March 15, 1946, American crews conducted a static firing test of a reassembled V-2 engine. The test revealed immediate difficulties. Fuel flow oscillations exceeded acceptable limits. Instrumentation readings showed vibration levels far above what American engines tolerated. Several valves leaked under pressure, not because the German design was flawed, but because American replacements lacked the precise machining tolerances of the originals. The first full launch followed on April 16, 1946. At 2:47 p.m., the V-2 lifted from its launch stand, rose unevenly, then veered off course. Within seconds, the guidance system lost stability. A tail fin separated. The rocket reached an altitude of approximately 3.4 miles before crashing into the desert. The failure was instructive and humiliating. Colonel Harold R. Turner, overseeing the test, summarized the situation bluntly. The United States possessed German hardware and German engineers, but not the German production ecosystem. Peenemünde had conducted over 6,000 test firings and combat launches. White Sands had conducted one. Over the next 3 years, 67 V-2 launches were conducted by American teams. Approximately 68% were classified as successful. In a laboratory context, the results were encouraging. In a military context, the failure rate was unacceptable. Each launch exposed weaknesses. Turbopumps failed due to microscopic imperfections in American cast alloys. Guidance systems drifted when gyroscopes lost calibration under vibration. Electrical connectors shorted under thermal stress. Cryogenic seals leaked when manufacturing tolerances slipped by thousandths of an inch. The V-2 was not forgiving technology. This was the collapse under pressure. American industry excelled at mass production, but it had never been asked to produce machines that operated simultaneously under extreme heat, vibration, pressure, acceleration, and cryogenic temperatures. Aircraft engines encountered some of these conditions, but never all at once, and never without human oversight. The German solution had been over-engineering backed by exhaustive testing. American design philosophy, shaped by wartime urgency and cost efficiency, had favored minimum acceptable margins. In rocketry, that approach failed repeatedly. The pressure intensified with geopolitical developments. By 1946, intelligence reports confirmed that the Soviet Union had captured Peenemünde itself, along with significant numbers of German technicians. Helmut Grothwup and his team were already working under Soviet direction. Test launches were underway at Kapustin Yar. The V-2 was no longer a defeated weapon. It was the foundation of a new arms race. Within the Pentagon, classified memoranda began using language that would have been unthinkable before Nordhausen. Ballistic missiles were now described as strategically decisive. Air defenses were judged ineffective
against high-velocity, high-altitude targets.
Existing doctrines offered no solution. The pressure was not only technical, but institutional. American rocket research before 1945 had been fragmented. Goddard worked largely alone. The Navy pursued small experimental rockets. The Army funded limited artillery rocket programs. There was no unified vision, no centralized authority, no sustained funding. The V-2 shattered that complacency. In 1947, the Army Ordnance Department made a decisive move. Redstone Arsenal in Huntsville, Alabama, was designated as a permanent center for ballistic missile development. German engineers were relocated from Fort Bliss to Huntsville under what would later become known as Operation Paperclip. Wernher von Braun, once a prisoner of war, now worked under American contract. This transition did not erase the technological gap overnight. The first American missile, derived directly from the V-2, was the Redstone. It retained the German engine architecture, liquid oxygen and alcohol propellants, regenerative cooling, turbopump feed systems, and gyroscopic guidance. Early Redstone tests revealed persistent problems: combustion instability, guidance drift, structural resonance. Each problem echoed a lesson learned years earlier by German engineers. The difference now was scale. Unlike Goddard's isolated experiments or the German wartime effort, Redstone development occurred within an expanding industrial framework. American companies such as Chrysler, North American Aviation, and General Electric became involved. Metallurgy improved. Precision machining advanced. Quality control processes evolved to meet rocket requirements rather than aircraft standards. Pressure forced adaptation. By the early 1950s, the failure rates declined. Launch reliability improved. Guidance systems became more robust. The technological gap that had once seemed insurmountable began to narrow, though it had not yet closed. The collapse under pressure produced one final transformation: purpose. Initially, American interest in the V-2 had been purely military. But the captured rockets offered something else: payload capacity, high-altitude access, a means of reaching space, even if unintentionally. Beginning in 1946, American scientists began flying instruments aboard V-2 launches: cosmic ray detectors, atmospheric sensors, biological specimens, cameras. On October 24, 1946, a V-2 launched from White Sands carried a 35mm motion picture camera to an altitude of approximately 65 miles. The recovered film showed the curvature of the Earth against the blackness of space. It was the first photograph taken from beyond the atmosphere. That image carried symbolic weight. The same weapon that had terrorized London now offered a glimpse of Earth from above. The collapse of American assumptions about military rocketry was giving way to an expanded understanding of what rockets represented. Still, the pressure remained relentless. The Soviet Union launched its own missile programs with speed and secrecy. Intelligence analysts warned that the window for American recovery was narrow. Ballistic missile technology could not be improvised in a crisis. It required years of sustained effort. By 1953, classified assessments concluded that the United States was no longer hopelessly behind, but it was not yet ahead. Parity had been approached, not dominance. The collapse under pressure had forced a reckoning. The V-2 had exposed not a failure of intelligence, but a failure of commitment. American science had possessed the theoretical foundations of rocketry. What it lacked was the institutional will to develop those ideas at scale before war demanded it. That lesson would shape every subsequent decision. Missile programs expanded, funding increased, research laboratories multiplied. Rocketry became a permanent pillar of national defense rather than a fringe curiosity. The pressure that once revealed American weakness now became the engine of adaptation. By the early 1950s, American rocket engineers no longer spoke about the German V-2 with disbelief. They spoke about it with familiarity. The shock that had defined 1945 was giving way to something more disciplined: institutional learning. The United States had recognized the depth of its technological deficit, absorbed the lessons embedded in German hardware, and begun the long process of adaptation. This phase was neither dramatic nor triumphant. It was methodical, bureaucratic, and relentlessly technical. At Redstone Arsenal in Huntsville, Alabama, Wernher von Braun's team worked under close military supervision, integrated into a growing American engineering culture that demanded documentation, redundancy, and reproducibility. German engineers brought experience. American engineers brought industrial scale. The fusion was uneasy, but effective. The Redstone missile, first tested in August 1953, embodied this adaptation. Standing approximately 69 feet tall and weighing over 60,000 pounds at launch, it was larger and more capable than the V-2, yet unmistakably descended from it. The propulsion system retained liquid oxygen and alcohol propellants. Regenerative cooling remained essential. Turbopumps still defined the system's complexity. But the differences mattered. American engineers redesigned components for manufacturability rather than artisanal precision. Alloys were standardized. Tolerances were adjusted to match American machine tools. Electrical systems were simplified and ruggedized. The guidance package, while inspired by German gyroscopic concepts, incorporated American advances in control theory and electronics. Failures still occurred. Early Redstone launches suffered engine shutdowns, guidance drift, and structural oscillations. Yet unlike the V-2 program, these failures did not halt progress. They were analyzed, documented, and corrected through iterative design. This represented a philosophical shift from wartime German urgency to peacetime American engineering discipline. By 1955, Redstone reliability exceeded 90%. That success had immediate strategic implications. The United States now possessed a short-range ballistic missile capable of delivering nuclear warheads. More importantly, it possessed an industrial system capable of building rockets reliably repeatedly, and at scale. Recognition of what rocket technology truly represented began spreading beyond the Army. The Air Force, newly independent in 1947, launched its own missile programs, including Atlas and Thor. The Navy pursued submarine-launched ballistic missiles under the Polaris program. Each service initially competed for funding and prestige, but all shared a common foundation: lessons learned from the V-2. The recognition extended beyond weapons. Scientific use of rockets expanded rapidly. V-2 launches from White Sands had already demonstrated the value of high-altitude research. Now, purpose-built sounding rockets carried experiments routinely above the atmosphere. Data on cosmic radiation, solar particles, and atmospheric composition reshaped scientific understanding. In 1951, a V-2 launched rhesus monkeys named Albert and Patricia to altitudes exceeding 40 miles. Earlier flights had failed, sometimes fatally. These missions reflected the experimental nature of early space research and the ethical ambiguities that accompanied it. The data gathered informed life support systems that would later support human flight. The adaptation phase also forced moral reckoning. Operation Paperclip remained controversial. Publicly, German engineers were described as technical specialists. Privately, military officials acknowledged their involvement in the Nazi war machine. Investigations revealed varying degrees of complicity, including awareness of forced labor at Mittelwerk. Yet the Cold War context dominated decision-making. By 1950, the Soviet Union had detonated its first atomic bomb. Intelligence estimates suggested rapid Soviet progress in missile development. The calculus was brutal. Denying German expertise to Moscow outweighed moral objections. This recognition shaped American policy for decades. Funding for rocket research increased dramatically. Universities established aerospace engineering departments. Private industry expanded into propulsion, guidance, and materials science. Rocketry was no longer experimental curiosity. It was national infrastructure. The culmination of this adaptive process became visible in January 1958. On January 31st, Explorer 1 launched atop a Jupiter C rocket derived directly from Redstone technology. Designed by the Army Ballistic Missile Agency under von Braun's leadership, Explorer 1 carried a scientific payload developed by James Van Allen. It discovered the radiation belts surrounding Earth, a fundamental finding in space science. The launch was not smooth. Earlier attempts by other programs had failed publicly, embarrassing the United States after the Soviet launch of Sputnik in October 1957. Explorer 1 succeeded not because of haste, but because of the accumulated discipline forged through years of adaptation. The missile worked. The payload functioned. Data returned. The recognition phase was complete. America no longer measured itself against German wartime achievements. It measured itself against the frontier of space and the strategic demands of the Cold War. The V-2 had been a starting point, not an end point. What followed would no longer be reactive. In 1958, the National Aeronautics and Space Administration was established. Rocket development shifted from purely military institutions toward a civilian agency with a mandate that extended beyond weapons. Space exploration became a national objective rather than a byproduct of military necessity. The adaptation had succeeded because it had been honest. American engineers had accepted that they were behind. They had resisted the temptation to dismiss German achievements as anomalies or moral aberrations. Instead, they studied them, replicated them, and improved upon them. Robert Goddard did not live to see this transformation. He died in August 1945, months after examining the V-2 in Annapolis. But his ideas lived on, embedded within systems far larger than anything he could have imagined. Recognition led to adaptation. Adaptation laid the foundation for transformation. The final stage would redefine not only military power, but humanity's relationship with the planet itself. By the end of the 1950s, the transformation was complete. What began in 1945 as shock and embarrassment inside dim warehouses and desert test ranges had evolved into a permanent restructuring of American power. The German V-2, once a terror weapon aimed blindly at cities, had become the catalyst for a new strategic reality. The United States had not merely caught up, it had redefined the meaning of technological leadership. The consequences extended far beyond rocketry. Ballistic missiles fundamentally altered warfare. For the first time in history, distance ceased to provide security. No fleet, no air defense network, no border fortification could reliably stop a weapon traveling thousands of miles at hypersonic speed. The V-2 had demonstrated this principle brutally over London and Antwerp. American planners understood immediately that the next generation would carry nuclear warheads. By 1957, both superpowers possessed the capability to strike each other's cities within minutes. Deterrence replaced defense. Strategy shifted from winning wars to preventing them. This change reshaped every branch of the American military. Air power no longer meant bombers alone. Missiles became central to strategic planning. The Air Force built intercontinental ballistic missile forces around Atlas and Titan. The Navy embedded nuclear missiles aboard submarines that could remain hidden for months. The Army, once the driving force behind early rocketry, ceded much of the mission.
Technology scaled upward. The industrial consequences were equally profound. The requirements of rocketry accelerated advances in metallurgy, electronics, quality control, and systems engineering. Factories learned to build machines that could not fail, because failure meant catastrophe. Tolerances tightened, testing regimes expanded. Documentation became as important as design. Entire industries emerged from these demands. Aerospace engineering became a dominant field. Guidance systems evolved into modern control theory. Miniaturized electronics developed from missiles fed directly into computers and communications technology. The supply chains created to support rockets reshaped American manufacturing. None of this would have occurred without the recognition triggered by the V-2. The space race followed naturally. When the Soviet Union launched Sputnik in October 1957, the psychological shock echoed that of 1945, but with a crucial difference. This time, the United States possessed the institutional framework to respond. Explorer 1 followed within months. Human spaceflight programs accelerated. Mercury led to Gemini, Gemini to Apollo. In July 1969, a Saturn V rocket lifted Apollo 11 toward the Moon. The lineage was unmistakable. The Saturn V's 5 F1 engines produced 7.5 million pounds of thrust. Each engine alone generated more than 25 times the thrust of a V-2. Yet the design principles were familiar. Regenerative cooling, turbopump-fed propellants, gyroscopic guidance, thrust vector control. Concepts first proven in wartime Germany had been scaled, refined, and transformed by American industry. When Neil Armstrong stepped onto the lunar surface, he did so atop technology that traced its ancestry back to Peenemünde and Mittelwerk, and to the moment American engineers realized they were behind. The moral consequences were never resolved cleanly. Operation Paperclip left a permanent ethical stain. The same expertise that enabled peaceful exploration
had been forged in a system that exploited slave labor and served a genocidal regime. The rockets that carried astronauts to space shared DNA with weapons that killed civilians and prisoners alike. American leaders chose pragmatism over purity. The Cold War demanded it. Yet the long-term outcome diverged sharply from the V-2's original purpose. The weapon designed to terrorize cities became a tool for scientific discovery. Space telescopes, planetary probes, weather satellites, and global communications systems all emerged from the same technological foundation. The V-2 failed as a strategic weapon. It succeeded as a technological seed. For Robert Goddard, the story carried bitter irony. His early work had anticipated many V-2 principles: liquid fuel propulsion, gyroscopic stabilization, controlled thrust. Yet without institutional support, his ideas remained limited in scale. Germany proved what could be achieved when a nation committed fully to a technology, for good or ill. America learned that lesson the hard way. After 1945, scientific research became a matter of national policy. Funding expanded, laboratories multiplied, universities partnered with government and industry. Innovation was no longer left to isolated individuals. The strategic consequence was dominance. By the late 20th century, the United States controlled access to space, global navigation systems, satellite reconnaissance, and long-range strike capability. These advantages shaped diplomacy, warfare, and global economics. All of it traced back to a single realization: falling behind was unacceptable. The warehouse in Annapolis where Goddard examined the V-2 no longer exists. The desert launch pads at White Sands remain, weathered by decades of testing. Peenemünde lies quiet, its ruins visited by historians rather than engineers. But the consequences of what happened there remain alive. The V-2 taught America that technological neglect carries strategic cost, that innovation requires sustained commitment, that the future belongs not to those with the best ideas alone, but to those willing to build systems capable of turning ideas into reality. In the end, Germany lost the war, but won the opening chapter of the Missile Age. America lost that chapter, but wrote the rest of the book. The wake-up call delivered in 1945 reshaped military power, industry, science, and humanity's reach beyond Earth. It proved that even profound technological gaps can be closed, but only by those willing to recognize them first.